A right-tailed hypothesis test about a population proportion. In this example, suppose that historically 42% of all Stat 205 students have made A's or B's. With recent changes, I would like to know if the percentage has increased. A random sample of 400 grades in Stat 205 is collected. Among these, there were 178 students who earned an A or a B. Using a 0.05 level of significance, does this indicate that the changes have resulted in a higher proportion of Stat 205 students making A's or B's? We can begin by recognizing that the parameter P represents the proportion of all students taking Stat 205 who make an A or a B in the course. The next step is to identify the null and the alternative hypotheses. H sub 0 will be that the parameter P equals 0.42. This is the historical value given in the example. Next, the alternative hypothesis is what I want to know if the data supports. In this case, I want to know if the percentage has increased. So as a proportion, that would be that P is larger than or is greater than 0.42. Next, we identify the alpha value or the level of significance and state the decision rule. So here we will use alpha equal to 0.05 for the level of significance. The decision rule can then be stated if the p-value or the probability we find is less than or equal to 0.05, then the decision is to reject the null hypothesis H sub 0. Otherwise, we fail to reject the null hypothesis. The test statistic comes next. In this case, we begin with the formula. So you can see p hat minus p is the numerator. The denominator is the square root of p times 1 minus p divided by the sample size n. Substituting the values, we would get 0.445, that will be the sample proportion, minus 0.42, that's the value of the population proportion, the parameter, if the null hypothesis is true. So what we're doing is taking this value from H sub 0 and substituting 0.42 for P. In the denominator, underneath the square root, we have the proportion 0.42 times 1 minus that number, which would be 0.58, then divide by the sample size of 400. Remember, we took a random sample of 400 grades of students. Calculating those out, in the numerator we get 0.025, in the denominator we get 0.024678. When you calculate that, you see that the z-score, rounded off to 2 digits after the decimal point, will be 1.01. Notice the sample proportion. The first number in the numerator, 0.445, comes from the fraction 178 divided by 400. Next, we want the probability. Now the probability is going to be the chance we get the observed value or one more supportive of the alternative hypothesis, one that would make me even more strongly believe the true population proportion has increased. So we're going to the right of the z-score we found. So we want the probability a z-value is greater than 1.01. Remember, our table z gives us the area to the left of the number we look up. So when we look up 1.01, we get 0.8438, but that's the area to the left. We want the area to the right. So we do 1 minus that number and get that our probability is 0.1562. Now in our next step, we want to look at our probability we calculated and apply the decision rule to make our decision, and then write a summary or a conclusion. So I decide to fail to reject H sub 0, the null hypothesis, because 0.1562 is not less than or equal to 0.05. In summary, I could say, using a 0.05 level of significance, there is not significant evidence to conclude the proportion of all students taking Stat 205 who make an A or a B in the course is more than 0.42. Note, this is an example of what is called a right-tailed test. Why is that? Because values in the extreme right tail of the normal distribution would support the statement in the alternative hypothesis that the proportion or the percentage is more than it used to be. Now, as far as the validity check, okay, basically we're going back and asking, does this z-score really produce a standard normal random variable? Okay, we look for a random sample of categorical data. So we take a random sample of students that were selected and they were categorized, right? A success or having the characteristic meant they made an A or a B in the course. N times P, the sample size was 400. P, if the null hypothesis is true, that's what we use for the hypothesis test, is 0.42. 400 times 0.42 is 168. So I expect 168 successes or 168 A or B grades to happen if the null hypothesis is true. And remember, that needs to be at least 10. Okay, 168 is at least 10, so that's okay. And then N times Q, or N times 1 minus P, okay, is 400 times 1 minus 0.42 is 0.58. Okay, and notice that's the same number in the denominator of your z-score calculation. That turns out to be 232. That number also needs to be at least 10 in this case. Okay, so all three conditions are met, so the hypothesis test is valid. Now, let's go back and look at a couple of new definition applications that we haven't gone over before in an example with a hypothesis test at the end. A type 1 error, by definition, is when you conclude the alternative hypothesis is true. In this case, we would be saying P is more than 0.42, when in fact the truth is that the null hypothesis is correct. Okay, so what that would look like in this case would be that a type 1 error would be to conclude the proportion of all students taking Stat 205 who make an A or a B is more than 0.42, when the truth is that only 0.42 or less of all students taking Stat 205 really make an A or a B. Now, a type 2 error would consist of concluding sort of the opposite error is what you're doing, concluding the null hypothesis is true when in fact the alternative hypothesis really is true. So in this case, a type 2 error would be concluding that the proportion of all students taking Stat 205 who make an A or a B is 0.42, when the truth is really more than 0.42 of all students taking Stat 205 make an A or a B. Okay, so these are a couple of applications of just the type 1 error and type 2 error in terms of a scenario. So once I have a null and an alternative hypothesis, I can talk about what these errors would look like, and then if I wanted to, think about consequences and so on for those.